Okay, class, so today we're going to look at a couple of things that go along with your review for logarithms. So I'm going to first start again by talking about what is a logarithm, right? Well, it all starts back with our inverse functions. So right now I have the function y equals 10 to the x power. So we've been studying inverses, and one of the first things I hope you remember about inverses is that we're looking for a function that's invertible. So I first want to know is y equals 10 to the x, this basic exponential, is it an invertible function? And so I kind of look at it and go, oh, maybe, but it helps to have a graph. So I'll do a quick sketch. 10 to the x is an exponential pattern, meaning you're multiplying by 10 for every 1x you increase. Or divide by 10 if you're going to the negative values. All right, but it ends up looking somewhat like this. Okay? And that function right there shows that for every input, I have one output. That makes it a function. But what makes this an invertible function is that if I choose a y value, there can be only one x value that maps to that value. So I'll give you, for instance, if I chose this y value right here, I don't know what it is, doesn't matter, I'm just choosing a y value. That y value is the same across this whole horizontal line. If you look, that horizontal line only intersects the 10 to the x function in one place, right here, which means this x value right there maps to that y value, and it's the only way to map to that y value. That makes this function 1 to 1. Now I know you proofers out there are saying, hey, that's only one example. That's not a deductive proof. But if you study the 10 to the x pattern, you will find that this function cannot have repeated y values, and it will in fact be 1 to 1. That means it must have an inverse. Well, let's see what happens. If you have to have an inverse, one of the methods, the algorithms we use to find an inverse is to switch the x and the y values. You switch the domain with the range, which means the inverse function takes the range from the original function as its new domain. Well, algorithm-wise, this becomes a switch of the x and the y. So I'll have x equals 10 to the y. The next step in our algorithm we used in class was to try to solve this for y, to get an explicit equation for y equals something in terms of x. That would be very useful. We could then use that as its inverse function. But here's where mathematicians said, wait a minute, we don't have an algebraic way for solving this. I can't just divide by 10 because 10 is being raised to some power of y. I can't subtract 10 because, again, 10 is being raised to a power of y. We're kind of locked. What do we do? So the mathematicians invented something called the logarithm. What you see here, x equals 10 to the y, is the logarithm, but we rewrite it like this. Y equals, remember we want an explicitly solved y equation, so y will equal the logarithm, and the full written word is logarithm, like so. The mathematicians don't write out logarithm every time, they just write log. And it has the same base as this exponent does, so that base is written in subscript notation beneath there, and it's the logarithm base 10 of x. These two expressions are equivalent to each other. What I like about saying they're equivalent is saying that they have to have the similar properties too. So if I have exponential properties that work for exponents, there will be some kind of corresponding logarithmic property that goes along with it. But this now is the inverse function to the original y equals 10 to the x function. That's good to know. But that gives us a lot of opportunity to use the inverse function as a way to undo a base 10 exponential. I'll give you, for instance, not using exponentials. If I had the function x squared equals 9, you as algebra students at this point in time know how to solve for x. You would undo the square with the square root. Because you know the square root function and the squaring function are inverses with a restricted domain, only the positive x values. This would become an answer of x equals 3. Again, if I restrict to positive x values. So the square and the square root function, as you see, cancel out to leave just x. Well, that's the glory of the logarithm function. When I start to use this as an inverse function, if I say 10 to the x equals 25, the logarithm function allows me to undo this base 10. I could apply the logarithm, base 10, to both sides of this equation. And on this side, the logarithm base 10 and the base 10 exponential cancel as inverses, leaving just x equals the log of 25 base 10. At this point in time, I'll leave it like this. Eventually, we'll be putting these in our calculator and getting decimal approximations. But logarithm is the inverse to a base 10 exponential.